Welcome back to this video on S2. In this video we're looking at approximating a binomial distribution, unit 3.2. Now in the last video we looked at approximating a binomial distribution by using a Poisson distribution. In this one we're actually going to look at approximating a binomial by using the normal distribution, which we learned all about in S1. Let's first consider the normal distribution. So if you remember from S1, very quickly, it's not the best diagram, but we have a graph shape something like this. Often people will talk about this as a bell curve. And what's important about this is it is symmetrical. Both sides, there's symmetry about that middle. And on a perfect one, then that middle would essentially be that mean, wouldn't it? That mean value. And our normal is mean and its variance. And that is obviously, quite important. Now, for us, looking at the binomial, well, when or under what circumstances could we use the binomial? Well, it's quite simple really. We can use the binomial when p is a half or as close to a half as possible. So if p is close to a half, that would then give us a symmetrical graph, and then what we would then need is a large value of n. The larger the better, okay, just to then make it essentially as close to a normal distribution as possible. So I'll just make a note of those. So n is large and p is close to 0.5. Now to find the mean, that's going to be n times p, and to find the standard deviation, or let's go with the variance, that'll be np1 minus p. Obviously these we're already aware of, especially we were going through them in the last video. Now in the last video, when we looked at the binomial and we approximated it with Poisson, I said a good rule of thumb was if np is less than or equal to 10, and n is obviously large and p is small, then you should use a Poisson distribution. Now by that same kind of logic, this is the only other way of approximating binomial in A-level statistics. So what you need to do here is, if np is greater than 10, then it should be using a normal approximation. So less than or equal to 10, Poisson; more than 10, normal. That will be your general rule, your rule of thumb. Okay, not perfect, but should give you a really good idea. Now, why do I tell you this? Well, ultimately it's this whole p being close to a half. I've seen questions in the past, granted on some of the older papers, but I've seen questions in the past where that value of p is not really close to half. It might be like 0.3 or something like that. So it is quite important to kind of work out your NP, your mean, and use that just to help guide you. Okay. Now, why do we approximate binomial with normal? Well, it's quite simple. We didn't always have these calculators that could do a lot of this work for us. So when you're doing your A-level, normally you go in your tables go up to n equals 50. What do we do when n is values larger than 50? And that was kind of part of the problem. We couldn't deal with it in terms of what we had available in A-level. So, in those types of questions, when you see that n is greater than 50, then there's a huge implication there that you're probably going to be using a approximation, whether that's Poisson or normal. Now, the next thing I need to talk to you about is what's called continuity correction. What is it and why do I need to apply it? Well, quite simply, we're going from two different types of data. Binomial distribution is discrete data, isn't it? Whereas normal distribution is continuous data. And so I need to apply this continuity correction when I'm moving from discrete data into that continuous data. So in kind of layman's terms, say I have a value of x is 14, or say I'm looking at x is less than or equal to 14 or greater than, but whatever I'm looking at, in terms of my discrete data, my binomial, there are specific values either side of that, aren't there? However, with a normal distribution, that's continuous, so it includes the values that come in between them. So what I actually need to do is consider those values that are in between. And it kind of comes down to where you're looking at less than or whether you're looking at greater than in terms of where you need to go. So if I was looking at, say, the probability when x is less than or equal to 14. Now, if this is on my binomial, then when I come to my normal, I would need to look at less than or equal to 14.5. I suppose technically you can think of it as just less than that 14.5, can't you? Because it's this 14, and anything just bigger than the 14, like 14.1 for example, would still round to 14, therefore should still be included with my normal. So it's all the way up to this 14.5. So that's what I've got then with my normal. And equally, if I was looking at something that was greater than, so if we do x is greater than or equal to 14, then in terms of the normal, that would be greater than or equal to 13.5, wouldn't it? Because it would be everything below here would round to this one, and because we're going in this direction, we need to include this as the essentially the smallest possible value, because that's the smallest possible value that will still round to 14. And that is essentially what we're doing with this continuity correction. You go in 0.5 either above or below the line, or sorry, above or below the value of x that you want, your variable, your random variable, and it really depends on whether you're looking at a greater than or a less than. Now, you'll start to see, in this one, when I talk to you a lot about always converting to greater than or equal to or less than or equal to, you'll start to see the benefits of it with our continuity correction. I think the best thing to do now is to look at a couple of examples. In this example, we can see that n is 150, p is 0.45, so n is large, p is close to a half. So a suitable approximation will be a normal approximation, because obviously this being closer to a half would mean that it's unlikely to be Poisson. First thing I want to do is find out what n times p is. So straight into my calculator, 150 times 0.45, and that gives me 67.5. You can see that's much bigger than 10. Definitely no doubt that this is a normal approximation. So I'm going to call it y, and normal, and then my NP is 67.5. And then I want to find my variance, don't I? So my variance, so this was our mean, wasn't it? And our variance is NP1 minus P. So I've got 67.5 times 0.55. So 67.5 times 0.55. And that will give me 37.125. So 37.125. You can also square root that if you prefer. This case doesn't make much sense, but sometimes it's easier to square root it and then leave it with a little squared sign above it, so that you have that value of standard deviation, which is what you need in your calculations, isn't it? Next, I'm just going to make a bit of room and we'll start with this first part A. So we're looking at x being less than or equal to 60. And what we want to do here is essentially we want to approximate this with y. So we're looking at y being less than or equal to. It doesn't actually matter with normal distribution, but it's going to be 60.5. Because remember, you're thinking of 60, you want less than, so you need to go as far as that 60.5, because all the values on this right hand side here, they all would round to give you 60. So that's what you're thinking of. Now that we've got what we're trying to work out, it's just a matter of essentially using, your S1 knowledge, isn't it? So for that, you need to find your value of Z, don't you? If I just think of the diagram, we've got 67.5 in the center. We want less than 60.5. So this is what we're looking at. So we're actually going to end up with something this side, and we're going to end up with a 1 minus. So let's find that value of Z. Now, if you remember, Z is mean minus, totally wrong there, x minus the mean over the standard deviation. So in this case, that's 60.5 minus 67.5 over the square root of 37.125. And that gives me minus 1.14885, and so on. If you think about your tables, 1.15, because 2 decimal places is what you're going to be able to look up in your tables. So that means that this value here is my minus 1.15, which means this value here is a positive 1.15. So that's what I'm going to kind of write here. So this is the same as Z being less than minus 1.15, which is the same as 1 minus the probability that Z is less than 1.15, as in the positive one. So you can see from here that less than negative 1.15 is the same as greater than 1.15, which is 1 minus. So, if you wanted me to take in the extra step, we would have this line in there, and then finally my 1 minus probability is Z is less than 1.15. So that's kind of the steps of what I'm doing. And I do think it's always worth kind of writing these out, whether you're writing them out like I have here with your diagrams, and just really making it clear to make sure you get the marks for this type of question. As I have seen, where students use the calculators a little bit too much and perhaps don't put down enough of their method and how they get into their answer and really showing off their knowledge. So, it does, in cases, it could, affect your marks in a question. Now I've just cut out the values out of the S1 tables here. So we got 1 minus 0.8749. So So 1 minus 0.8749, and that's going to give me 0.1251, which I'll do to 3 significant figures, especially since it's an approximation. The best thing about having a Casio 991 or 570 class widths means that you can also check this by using the actual binomial values. So I've just checked this one out here, and in my calculator it's given me 0.1250822 and so on. So you can see here it's 1251, very close, or exactly the same as ours. And again, obviously it will round to the 3 significant figures there. So it's very, very useful to have the calculator, but obviously you should be relying on the methods, essentially the methods from the tables. Whether you use your calculator in some steps or not, you know, you should really be comfortable using your tables. Part B. So in this one we're looking at x being greater than 75. And as I've said all along, make sure you write this as equals. So this would be greater than or equal to 76. And that, again, as I've said before, is really important, and this is where it really helps make sure you cut out your mistakes. So we want greater than 76, which means that we're looking at 75.5. So that's where we're going, greater than that 75.5. So in terms of my y, my normal, we're looking at greater than or equal to 75.5. And that's why it's important, because if you change it to equals, you won't make these mistakes. The mistakes that I see people make because they try and do it straight from here, and it just gives them more things to remember and therefore more things where they can go wrong. Now from this point onwards, let's look at a quick sketch of our normal. We know that the mean is 67.5, so 75.5 has got to be after that mean, and we want greater than, so that's what we're looking at. This should be nice, easy to do. So let's find our z value. It should be positive, so 75.5 minus 67.5 over the square root of 37.125. And that gives me 1.31297 and so on. So the value we'll be using is 1.31. I'll pop that on here in red, 1.31. And again, you know, this was actually an easy one, isn't it? You know, but I want to write down my steps over on the left here. So this is now the same as, instead of y, it would be z being greater than or equal to that 1.31, which is the same as 1 minus the probability that z is less than 1.31. Remember, for this, for normal distribution, it doesn't matter whether I put an equals or not, it's going to mean the same because it's continuous. So same as before, I've just popped the values down here from the tables, just cut them out there. So 0.9049, and that gives me 0.0951. Now, as I did previously, I just tell you what the value is from the calculator based on the actual binomial. Comes out at 0.0948371. So you can see here, you know, this is 0.0948 to 3 significant figures. So very, very close to our value. Obviously, we're not expecting it to be exactly the same, certainly in every case. But again, you know, it's a very, very close value, perfect approximation. You have the idea now, so it should be quite straightforward for part C. We are looking at between 65 and 80 inclusive, aren't we? So we need to change this into our Y, our normal approximation. So we're looking first at greater than 65. So again, I'm just going to do this kind of visually so you can see when you want greater than, you need to go below it, don't you? So 64.5. And then we're looking at less than 80. And that's when you kind of have to go past it to that 80.5, isn't it? Now I'm using just the, what I would expect, greater than or equal to because of the half, but technically less than. But as I've said numerous times, normal distribution is continuous, so whether it's got an equals or not is irrelevant. Now, anytime I'm using normal, I'll always do a sketch, whether I think it's an easy question or not. I think it's really important to do a sketch, to visualize the question, and to make sure you don't get it wrong. I think you do this enough times, then you actually can visualize that sketch in your head. You don't necessarily need to write it down, but I would always still write it down. But that's just me. I just think that, approaching everything methodical in that kind of way, setting things out visually, just makes your life easier. So you can see here, this is what we've got. We've got between these two values. Let's go ahead and find our values of Z for them. So I'll do that now. And that gives me 2.13 for my top value and minus 0.49 for the lower value there. Now, how do I go about working out what I'm actually going to do here? Again, as always, let's do some sketching. So what you're thinking about is that if you think about the large value first, this 80.5, which is my 2.13, we've got that very large value there. Less than that would give me all of that. We actually want to cut off this bottom bit, don't we? Yeah. So to cut off this bottom bit, we want less than this. Yeah. So we actually want to cut off, if you think about it like this, we want to cut off that minus 0.49, don't we? And doing that means that we would need to flip this. So 0.49 as in a positive, and that's a 1 minus it. Okay, so what we've actually got is less than this minus this. So let's write that down. We are looking at the probability of y being less than my 2.13, subtracting the probability that y is greater than 0.49. And from these sketches, I think it should be obvious, isn't it? Everything to the left, subtract this bit, and to find this bit I need to look at the symmetrical version of it and do 1 minus now. So this is going to give me y less than 2.13 minus, and we got 1 minus the probability that y is less than 0.49. So we've got the probability that y is less than 2.13 minus 1 plus the probability that y is less than 0.049. And all that's left to do now is to look these values up in my tables. So here you can see that we've got a 212 and then a 214. So 213 is going to be in between these two values. So we can put it as 0.9834 minus 1 and then plus 0.6879, and all that's left then to my calculators, and that leaves me 0.6713, or 0.671 to 3 significant figures. And again, I've done this in my calculator, and I've got 0.671294, or 0.671 to 3 significant figures. So this is my from calculator here. You can see that again, this one is pretty much bang on. So really happy with these approximations. Now, in this example, the first thing to do is determine what distribution we're looking at, and obviously this is binomial, as this is what the video is about, but you need to be able to spot this as well. So 70, and the probability is 0.5, as it is a fair coin there. In terms of an approximation, it's obviously going to be normal because we've got n is large and p is close to a half. Well, it's bang on a half, isn't it? Now we're looking at what the probability is when x is more than 45, so greater than 45. So let's first look at y. So we can approximate this. We know with the normal distribution, we want to find out what NP is. So that's going to be 70 times my 0.5, which is 35 there. And then we also want to do our NP1 minus P. So that's going to be our 35 basically times by a half again, isn't it? So 17.5 there. And of course that is our variance, isn't it? Didn't put it in over there. Now let's look at our y. So before I go into my y, let's make my x greater than or equal to 46. And then we're going to use our approximation. So we're going into y's now. And this is going to be greater than or equal to. And again, just if you're in doubt, just sketch it out. So we've got here, we're looking at greater than, so it's got to be everything that rounds up to this 46 that's still involved. Because we're going in this direction, if I picked 46.5, I'm obviously missing out loads, including 46 itself. So it's got to be this 45.5. So we're looking at 45.5 there. After that, I like to do a little sketch again, a little diagram. We know that in terms of the mean, that's 35, isn't it? And we're looking at 45.5, so it's got to be on the right of it, and we want greater than that value, don't we? So that's what we're looking at, which means that we're going to end up just doing a 1 minus this. So I'll pop to my calculator. All you need to do is find your value of z. So 45.5 minus 35 over 17.5, but it's the square root of it, isn't it? Because what I've worked out here is the variance. So pop that in like that so you can remember the variance and the mean there. And we get a value of z that is 2.51. It's actually 2.50998, but 2.51. Which, as you can see from my tables, is incredibly infuriating. I just want to be able to look up 2.51, but I can't. Now, what do you do if you get yourself into this kind of situation? Well, easiest thing to do is to kind of roughly work out what that 2.51 is. So between this and this, there are obviously 5 values. So all I've done is find the difference between these two. So this one, take away this one, divide it by 5, splitting it up into 5. Once I got that value, I added it onto this one. So that gave me a Z value of 0.99396. So if I come back to my tables, sorry, I've started writing in purple and we don't want that, do we? So we actually want 1 minus when y is less than or equal to 45.5. So we got 1 minus 0.99396, which 1 minus that is very small, isn't it? Oh, 0.00604, tiny. Now again, I'm checking in my calculator here, and I get 0.0057632. So you can see here, this is very, very close, isn't it? 006, 00, this would round to 6. So, you know, to one significant figure, these would be bang on. So happy with that. Now, if you're using the Edexcel IAL S2 textbook, and I did one of these examples, both of these are questions from there that I've borrowed as examples here. If you're using that, you might notice, like in the first example, one of the answers was, I think the first answer was 0.1251 for us, but in the textbook you'll see that it's 0.1253, and the reason for that is simple. They've used the calculator value, but they've used it doing the normal distribution, whereas obviously I've used the tables to find the estimate, and when I use the calculator I use the actual binomial values, which is obviously more accurate. They use the approximations but use the calculator to get the normals. Hopefully that makes sense, but you may notice as you do this exercise or any of these questions, when you come to them yourself, trying them from the textbook, you will notice that sometimes your values might be slightly different to those in the textbook. There's nothing wrong with that, it's just a slightly different ways of doing it sometimes. But you know, I feel if you're going to do the approximation, you need to be pretty competent at doing it with the tables here. Anyway, let's get into a few questions, and as always, I'll put the answers at the end. It's worth noting at this point, although doing this method you are doing a little bit of rounding and you are using your values from the tables, but if I use this original piece of data in my calculator using the binomial as in the original, what I get is 0.0558. So very, very close, or 558.5. So it'd actually be rounded off 0.0559 from my calculator. So you can see that it is still fairly accurate because n is large and p is very close to a half. Now if I read the question here, it's about first initially trying to work out whether this is Poisson or binomial. As in your S2 exam, that is what your choice is going to come down to. And we can see here that we've got this percentage. 40 hours is not that important right this second, and a random sample of 30 bits. So that's our n. Okay, the 40 hours is not as important at the moment because that's what we're looking at. X lasts longer than 40 hours. So we've got a binomial distribution here. So first thing I want to do is obviously set that up. So X is binomial. My value of n is 30 and my probability is 0.52. And this first part is just find the probability that X is less than 17. So probability X is less than 17 is discrete data, so I want an equals in there. So that's the probability that X is less than or equal to 16. So that's got to be my first setup. And then from here then is using what we did in the earlier chapters or units, unit 1. And I'm just going to do this in my calculator to save a little bit of time, but you can do it manually as well using the tables. And this will give me 0.6277 or 0.628 to 3 significant figures there. So that's just initially the same as what we'd done previously. It's part B where we come into the approximation. Now looking at part B, we can see that there is a slight change. Second random sample of 600 drill bits. So initially it was 30 bits, this time it's 600. Use a suitable approximation, find the probability that between 300 and 350 bits last longer than 40 hours. So let's this time call it Y, and that Y is still binomial. Its n is 600, and we can assume that the probability is going to stay the same. And you can see here that my n is very large and my p is close to a half. So from here I can go with the normal approximation. So finding my values for mean and standard deviation. So mean is NP. 600 times 0.52 gives me 312. And then the standard deviation is the square root of NP times 1 minus P. And that gives me 12.2 to 1 decimal place, so 3 significant figures, but I'll store the full answer in my calculator. Now let's look at what we're trying to find. We're trying to find between 300 and 350 bits. Now, for this one, we will be including those values, so the 300 and the 350. But what I could say is that, this kind of question isn't super clear. So, if you did actually use the ones that are between that, as in like the 301 and 349, then, they really should be giving you the marks there, because it's not explicitly clear that it is including those values. It's between those values, should really say inclusive of those values there. Anyway, let's apply continuity correction, and what we will get here is that it will now be between 299.5 and 350.5. And from here you should know what to do. But just remember, if in any doubt, I always like to do a little sketch. Doesn't have to be perfect. Okay, it's just there to kind of give you a little bit of guidance. So 350.5 is on the right, and then we've got our 299.5, which is actually on the left. So this is what we're trying to find. And you've got a couple of options here. What I would probably do is I would be finding just this half, so the 350 and less, and then take away 0.5 from it, and then the positive value of Z for the 299.5 and take away a half from it. In fact, let's do that now. I'll do it a little bit speeded up though. Now I've used the tables for this one, so the values from the tables. If you use purely a calculator, you will get a slight variation on this value. So in this question, again, we know what it is because of the types of questions we're looking at, but you are, when you come to the exam, going to have to be able to spot the difference between binomial and Poisson. So we've got this percentage here, and we've got a random sample of 100. And that should really be enough to let you know, because you've only got a choice between Poisson and binomial for these. So before I get started, let's go with X, and it's binomial. We've got 100 for N and 0.56 for P. The first part is not an approximation. So this again is like unit 1. Find the exact value of the probability that exactly 55 boxes contain a prize. So for A, we're looking at the probability when X equals 55. So if you go back to unit 1, and all you need to do there is use your binomial expansion. So kind of NCR. So we've got 155 there. We're going to multiply that by P, and that's going to be to the power 55. And then 1 minus P, so 0.44, and that will be the remaining value that totals 100, so that should be to the power 45. And then pop in that into my calculator, and I get 0.0784. This is the 4 decimal places. You could also do this. The 3 significant figures is the kind of gold standard for these questions. Now, part B is a little twist on our approximation. It's telling us to use a normal approximation. Okay, so we don't have to work that out, but it is obvious because close to half, fairly large. But it's asking us to find the percentage error. So it means we need to take the normal approximation and then find the percentage error between the two values. So first, let's find the mean and our standard deviation. So my mean is obviously 56 and my standard deviation is 4.96 there. I've done it to 3 significant figures. And if you did want to write it down, we would have a normal approximation where we've got 56 and 24.64. Obviously that's the variance there rather than the standard deviation. Now when the probability that X equals 55, that's going to be approximately equal to the probability that it is between 54.5 and 55.5. And then you know what to do from here, but I'll just go straight ahead with the answer. And from my calculator I get 0.078627, which is 63. There we are. So we've done this to kind of an extra few decimal places there, but it should make it a little bit easier. In fact, I should really be doing it the same as my answer to part A. Now, you should, if you're comparing these, have the same kind of rounding. I'm actually using the full values, so I'm actually going to use the full values. So we should have our largest value, so 0.07863 and so on, minus my 0.0784 and so on. It's actually 38 and so on, over the original, which is the proper value. So I'm using my actual full value. So this is my percentage error. And once I've done that, I must remember to multiply by 100. And this will give me 0.31127 and so on. So 0.31% there. Okay, but it's important in these kind of ones to use the full values because it's just that small variation. So if I, go through what the actual values here, let's put it in purple. If this one was 0.078383 and so on. Okay, and it's that difference between, once we've done the 7/8, it's this section and this section that we're looking at the percentage error, and you can see there's way less than even 0.5%, isn't there? 0.31%. Hopefully you found this video useful. Don't forget to any questions in the comments. I'm sure actually there might be one. Just looking at this question, it actually said find the exact value, and that was kind of impossible. So again, it's just another badly written question, and I get these questions from actual past papers. So, you can see that sometimes you do get these ones where, an exact value should be an exact value, like it might be a surd of some sort. Anyway, hopefully you did, as I was saying, find this video useful. Please like, subscribe, comment down below, ask me any questions, and I wish you the best of luck. See you soon.